you. Thank you for coming. My name is Susan Avery. I'm the president and director of the WHOI Oceanographic Institution. And it is just wonderful to see this huge turnout for tonight's event on a hot summer evening when perhaps the ocean and beach were beckoning a little bit more. So appreciate the wonderful opportunity to share with you what the institution has been doing with respect to the Deep Horizon blowout. I would like to note that because of the crowds, we do have to keep the side aisles open. So please don't crowd that for safety issues. Also, for those of you who are standing in the back, we are webcasting it, or you can see it in the conference room outside the lobby here. So if you'd like to go over there and be a little more comfortable, feel free to do so. We are live webcasting tonight, and several members of our Deep Submergence Laboratory who are at sea and aboard the research vessel Atlantis are tuning in from the Pacific. So for those of you in the Pacific, welcome and glad to have you with us tonight. Thank you. You will hear this over and over and over again, but every oil spill is different. You'll hear a little bit tonight about what makes the science of oil spills so interesting and complex, that it basically is needed to understand why these oil spills are different, how they behave in these different environments. And we're very pleased tonight, I'm very pleased tonight to have a great panel of scientists here who have been working not only on oil research over many decades, well, maybe not so many decades. Some of you are pretty young. Breck, maybe. Yeah, Judy, maybe. Well, we have that. You can see the transition is still there. Yeah, you like this. You might want to reverse, Jim. But also, they have been working diligently and have all been down in the Gulf over these last couple months. Research by the oceanographic scientist on oil includes work done here, right in Buzzards Bay. Many of you will have probably remembered the oil spill there. It's playing an important role in our ability to understand the science, the complex science of it. And I see John Farrington here from Emeritus. He's a real guru on oil spills. John, welcome here. Thank you. But what we are learning about oil in the Gulf is going to be important as it goes into our understanding of what our short and long-term response is. At the Oceanographic, our mission is to know the ocean. What does that mean? It means to know the physics, the chemistry, and biology of the ocean, how they work together, and how the ocean connects with its edges, the edges being our land, the atmosphere, the seafloor, and ice. We live the ocean is a very complex system, and it interacts with very complex systems, and it's obviously very critical for life on this planet as we know it. And understanding and looking at what's happening in the Gulf underscores that this knowledge is really critical and is essential in understanding what is happening down in the Gulf. Some of the science that you're going to hear tonight may sound like a CSI script. Some of it may sound like a Sherlock Holmes mystery. And some of it may come from an Indiana Jones adventure. Okay? But really, science is like none of those. And I think that hopefully you will tonight understand and get a little appreciation for what is really involved in scientific analysis. And it's not like a CSI, and it's not like a Sherlock Holmes, and it's not like an Indiana Jones, but it has certain elements of that. I really think that these panelists have really worked hard to put the pieces of the puzzle together and understanding what is going on, along with many other scientists who have been working in the Gulf recently. I really applaud them and their many colleagues from around the world who have responded to this event with an amazing dedication and professionalism, and quickly. And it's been a real pleasure to see the institution move forward in this direction. These panelists in particular, I want to thank for being here tonight. They have been running flat out since April, when this began. They had mobilized cruises in days, what would normally take months to do. and they've been putting in 20-hour days for long periods of time. They've been down in the Gulf, breathing the air down there, seeing the fires, and they've had first-hand experience. Their commitment is commendable, and it also is reflective, I think, of our shared vision at the institution of what it really takes to learn about the ocean and how that ocean sustains us and how we need to protect this precious resource that we have. Our moderator for tonight's panel is our Vice President for Marine Operations and Facilities, Rob Munier. Rob has joined us recently at the institution, and he's really come from us. He knows the industry really well. He knows project management, and he's been a key contact point in pulling all of this together. So, Rob, I'm going to turn it over to you, and let's get going on the panel.
Okay,
Thank you very
great.
much, sir. One thing, many of you came in early, and we do have copies of our magazine that are out in the lobby there, so if at the end you'd like to pick one up, please feel free to do so. Thank you. Now you can go, Rob.
Thank you, Susan. Fantastic turnout. Really appreciate that. It shows everybody's interest in this event, and obviously the interest here is extraordinary. We're professionals in the ocean business, but we're also lovers of the ocean. So this event is very important to us, both professionally and emotionally. And so we have taken with that tact our response to this and have worked hard to try and put something together tonight that we hope will be informative. The goal tonight is to try to give you a perspective of the oil spill from the science perspective. And the idea that we're talking about the WHOI in the Gulf would suggest that we've been fairly active, and we have been. And so our goal is to try and share with you some of the work that we've done and to answer some questions. And there have been questions out there. You've all had them. You've read about them. What was the flow rate? Was there a plume? If there is a plume, where is the oil? What's happening to the oil? Is it evaporating? Is it biodegrading? What's the effect of the dispersants? Is the oil coming up the East Coast? So these types of questions are the ones that we're working on trying to answer, and the folks here have been working on that. But these are works in progress. We don't have all the answers yet. Our approach to science here is very deliberative, and so we will not provide the answers until we've got all the data, done the analysis, and it's gone through the process of peer review and also met the requirements of the various sponsors that we've responded to. So we're in the middle of that process, and I guess I'd like to show this sort of timeline, which starts with April and ends where we are tonight. And so this is the 100-day. Today's the 101st day since the Deepwater Horizon explosion. And across the bottom, it shows some of the sort of main events that took place near the site. Some of them you've heard about, putting the containment dome on, when the top hat effort was tried, when top kill was tried, and then finally when the riser was cut so that the flow then was unobstructed for many days until finally the well was capped about 10 days ago. And during that time, there was a couple of tropical storms, Hurricane Alex and Tropical Storm Bonnie. So this was a very active time, and what were we doing there? Well, we were mobilizing to do a variety of different projects that are listed up there under the fieldwork heading, and some of it we're going to hear about tonight. But we were involved in making flow measurements. We were involved with doing traditional hydrography. We were involved with deploying a glider, and Breck's going to talk a little bit about that. We were involved with using an AUV to handle instrumentation that would allow us to make chemical measurements. We've deployed sediment traps to look at, over the long term, what the impact's going to be of the oil when it comes to the bottom. We took an oil sample, a sample of the effluent at the spill site, and are making preliminary analyses on just what that is going to tell us. And that provides a signature. And we're also looking at the plankton and the oil droplets. So we've been out in the field doing a variety of science and done it, as Susan mentioned, in a very short period of time. These are typically projects that you plan, and then maybe 6 to 9 months later you go out into the field, and then maybe 6 months after that you present your results. And we're in the process of presenting the results to these missions over the next few months. So this is happening on a very quick time scale. We've also been involved by supporting outreach in the community. And by doing that, we've attended and presented before Congress. And we've met with the White House Office of Science and Technology Policy. We've been involved with brainstorming sessions with Director Jim Cameron and with the Schlumberger Company, all in an effort to try and contribute what we have to offer here at WHOI. And one of the key things that we're really good at is working in deep water, and that was one of the unique things about this spill, is it occurred in deep water. And so not only do we have to worry about the oil on the surface, but we have to consider what's happening to the oil in the water column. And that's one of our areas of expertise. And one of the reasons we have that expertise is we have the ability to deploy technology. And our deep submergence capability allows us to take science down to deep water. And I think that's one of the things that has positioned us to be able to provide the types of response that we have been over these 100 days. What I'd like to do tonight, then, is to have our panelists each speak. So the format's going to be each panelist is going to speak for 10 minutes or so. And I'd like to hold questions, and then afterwards we will take questions. And what I would like to do is try to have questions at the microphones, and if you wouldn't mind lining up when we get to that point, and then in an orderly fashion we'll try and take questions. And I'll either deploy the questions to the right spot, or we'll huddle here and see who can come up with the best answer. So I'd like to introduce our first speaker. Our first speaker is Judy McDowell. She's at the right end of the table. You know what that means? And she got a PhD from UNH. She's been at WHOI for 35 years. She should have done that, sorry. She's a specialist in oil spills, has been working on oil spills for a long time, along with a lot of her other interests. And in fact, she wrote one of the books on oil spills, Oil in the Sea 3, that was published in 2003 for the National Research Council. So Judy, I'd like to have you come up.
Well, thank you all for coming to learn what we have to say about oil spills in general and what's been happening in the Gulf. I'd like to correct, I only coordinated the effects chapter for Oil in the Sea 3. Oil in the Sea 3 is quite an extensive volume. I didn't write the entire thing, but I think we are very proud of that volume, all of us who worked on it, and it pointed out many of the problems that we see today were highlighted in that book, and that was published in 2003. So forewarning of what deep exploration was going to involve and the problems they may encounter was highlighted and predicted, and here we are 7 years later with these problems that we see related to the Deep Horizon blowout. Well, my expertise is on physiological ecology of marine animals, and one of the things that interests me is the effects of oil spills, especially in the long term, on the marine environment. And oil comes into the environment by many different sources. And this cartoon that my colleague John Farrington and I published a couple of years ago in a paper identifies the various sources of oil to the marine environment. And as you can see by looking at this cartoon, that the amount of oil coming from tanker accidents or activities related to oil exploration are a relatively small percentage. A major component of oil introduction to the environment, the marine environment, comes from natural seeps. However, these are located in specific habitats. And because organisms may co-evolve with a natural seep, does not mean that the entire marine environment can cope with oiled habitats. And so I've seen many spills over the years that were very large in magnitude that had very minimal effects, and very small spills that had very major effects. And predicting effects of oil in the marine environment is largely dependent on the physical, chemical, and biological processes that you'll hear about this evening in determining where that oil goes and how contaminated a particular habitat becomes. We'll also talk about short-term and long-term effects. Now, many of you have seen this poor oiled pelican. It's been on the news almost every night for the past 101 days. And this is certainly a very significant effect, acute effect of oil. Wildlife becoming stranded in the slicks, their food resources, they themselves becoming heavily oiled, the components of oil right after a spill, many of the naphthalenes, benzenes, toluenes, many of the very toxic components are associated with acute toxicity. But oil can also have chronic effects. And this marsh from Windsor Cove in North Falmouth that George Hampson spent quite a number of years looking at the after effects of a barge spill, the Bouchard 65, which occurred in 1974. It's taken decades for this marsh to respond to that spill, and it has not yet fully recovered. So an oil spill can have effects on a matter of hours, days, and weeks, and those effects in some instances may be gone very quickly, but in other instances they may last months, years, even decades. I put this flow chart together to say what happens when we have an oil spill. There are several different pathways. The first on the top is initial oiling, and that's what happened with the Pelican. Covered with a slick, and other organisms may avoid the oil, so there may be no effect of the initial oiling. Other might have direct mortality, and then obviously they're removed from the resource population. Secondary release of oil. We know that there is oil subsurface. I was in Louisiana yesterday, and the headlines were, "Where's the oil? Don't see any oil anymore. Is it all gone? Or is there a reservoir subsurface that may come to surface the next tropical storm or next stratification event?" And so there can be secondary oiling. And that secondary oiling can begin to affect food chain resources, can alter the food supply, can have physiological effects on organisms. When altered physiology occurs, you may see reduced growth, you might see reduced reproduction, and so you begin to see changes in the populations, in the population structure. And the final step that can happen after an oil spill are the actual cleanup activities themselves. In the Exxon Valdez spill, the desire of people to go out and help with steam hoses on the rocky intertidal shore, steaming the oil off of the rocks, off of the habitat, probably had more effects on the habitat than maybe even the oil itself. And after the Amoco Cadiz spill, to remove the oil from nearshore sediments, they bulldozed the shoreline. And benthic organisms would not survive the bulldozing of total destruction of their habitat. So cleanup activities can actually reduce the quality of the habitat as well. And we need to be careful, when we are managing an oil spill, is to make sure that the solutions to the problem do not create a different set of problems. So to look at the Deepwater Horizon spill, today is the 101st day since the blowout. And in that period of time, 96 to 184 million gallons of oil have entered the Gulf of Mexico, depending on the range of estimates. Over 4,000 vessels have been involved in the cleanup. Over 4 million feet of sorbent in boom have been deployed to try to contain the oil. Close to 35 million gallons of an oil-water mix have been reclaimed. Over 57,000 square miles of fishing area has been closed, and much of the fishing area is closed because of the concern that resources may be contaminated. And finally, over 3,500 wildlife species, half of which are birds, coastal birds, including the pelicans we've seen, turtles and dolphins, have stranded and been found dead in the spill area. But the cause of death is not, in 100% of the cases, associated with the spill. Many of the cause of death is unknown. Now, from an educational perspective, the media has done a lot to try to address this problem and educate the public as what is going on in the Gulf, because it is of such concern. It's a national disaster. And I particularly like a suite of graphics that the USA Today has posted on their website. And I took a snapshot of one a week ago as I was preparing for this talk. I wanted to be on time. I had to go different places. So I took this snapshot of this interactive map a week ago today. And you can see the spread of the surface slick, the forecasted spread of the surface slick off the coast of Louisiana. And what this illustrates is that much of the impact has been restricted to the Louisiana coastline. There certainly have been tar balls washing up in other places on the Gulf shore, but much of the impact is restricted to Louisiana. And the gray areas along the coast throughout Mississippi, New Orleans, and even the tip of Florida are marshes, which can be, again, very vulnerable to oiling. So I suggest that you look at this map. If you look at the snapshot from today, you see very little oil, even on that coastal snapshot. The other interesting thing that, and I actually helped the USA Today reporter review some of the information that went into this graphic, is that when we look at resources that are at risk in the Gulf, we're not just concerned with the shallow water wetland habitats. You know, where the oil slick is going to come to shore certainly has a very dramatic effect, has an effect on tourism, has an effect on fishing, has an effect on just aesthetic concerns and emotional concerns that the public have. But we also need to be concerned, particularly with this spill, as you'll see from talk from the other speakers, that some of this oil is not just near shore, it's offshore. It's not just at the surface, it's subsurface. And those concerns make us as oceanographers, as ecologists, interested in what effect the oil is having, not just in shallow water habitats, but in deep water habitats, mid-water habitats, and what kinds of effects on the food chain may that be occurring. And so I divide up the concerns with the Deepwater Horizon spill in two areas. The surface plumes, which will have the near-shore impacts, the contaminated marshes, the wildlife strandings and wildlife loss, but also the subsurface plumes, which are offshore, deep water, and can have impacts on coral communities, can have impacts on midwater plankton communities, as well as other species in the midwater. So with that, thank you for your attention. I'd like to go into the rest of the panel and be happy to answer questions at the end of the panel. Thank you.
Thank you, Judy. She corrected me about the chapter in the book as opposed to the whole book. I was sort of speaking rhetorically, but really you shouldn't do that. And I think that was the point she was trying to make there. And even though we're very passionate about what we're doing and how we go about doing it, we have to be somewhat dispassionate about the facts. And we have to really just work with the facts. And I think while it's easy to be emotional and to have strong opinions about BP or the government's response or whatever, our approach really is to deal with the facts and then and let others make those types of judgments. I'd like to introduce Breck Owens. He's a physical oceanographer and a senior scientist. Breck's going to talk about the use of a glider to try and answer the question that I asked earlier about, where's the plume and where's it going. And his oil spill experience has been focused on this particular event. But he likes to study ocean circulation, and he is one of the experts on the loop current, which coincidentally is well located for this event. So he was able to interpret a lot about what the loop current effects might be, and he's going to talk to us about that tonight.
Thank you. Actually, yeah, I was actually working in the loop current for the previous 2 years. Turns out it was paid for by BP, coincidentally. They were interested in what's the loop current do for operational needs, and so they paid us to do that. Do we have the clicker? Thank you. So to start out with, I'd give you a little background and what's the oceanography, what's the physical oceanography of the Gulf of Mexico. Here we show the loop current. People hear about the loop current, and it's kind of a funny term. It's actually a current that's a warm current coming from the Caribbean, coming up into the Gulf of Mexico, makes a big loop, and then it goes out and exits past Florida and feeds the Gulf Stream. It's not always here. Sometimes it extends farther up, close to the well site, and does other things. It brings warm water. It's actually the reason. Oops, that was the wrong thing to do. We have a little animation here. The kinds of things that can happen to the loop current. It can start out. Sometimes there's little eddies form nearby and actually interact with the loop current, cause it to close off, form eddies. Here's a little animation of an eddy coming by, affecting things, and it'll cause it to pinch off. A little visualization here. Eventually, it will oftentimes pinch off an eddy that will form here. That eddy actually, over time, will actually propagate to the west over about 3 or 4 months, and in the meantime, the water that's come in from the Caribbean is no longer really going into the Gulf itself very much, but going directly out to feed the Gulf Stream, which means that this water is would be pure Caribbean water and would be far from the oil spill. So that's one scenario that we would hope would happen, if we're lucky, will happen for the case, and I'll show you some results later about that. In terms of the glider, there's a glider over there. Give you an idea what the size of it is. It's an instrument. It's autonomous, meaning it goes on its own. We only talk to it occasionally when we need to change its mission parameters. It makes a zigzag sawtooth pattern in the ocean, going from the surface to 1,000 meters, or 500 meters in this case, going about 3 kilometers between each sawtooth. It's kind of a fun instrument. It goes a long ways. They can go up to 4,000 kilometers, last 4 or 5 months. The glider we have now will go probably 1,000 or 2,000 kilometers, be out for 100 days. It measures temperature salinity. In this case, we actually have a acoustic sensor that will measure velocity, and it also measures how much scatters are in the water, whether it's plankton or whether it's small pieces of small oil drops. And that data is sent back in real time. It's basically email. It phones home with an email from the middle of the ocean, and we can actually phone back, send it an email to change its parameters. So I'm actually the glider pilot, but I do it from my desk, from my desktop computer. I've done it from my iPhone too, but mainly from my desktop computer. So here's again a picture of a glider that we launched off Martha's Vineyard and recovered in Bermuda, went across the Gulf Stream, which is really good practice for going through the loop current, so we can control it through really strong currents. And it's a little tricky, but we've done pretty well. In terms of the data that we're getting from the Gulf of Mexico, here's a plot of the track so far. We started out here on the shelf, came down, and then we coordinated with 2 other gliders that were out at the same time to make a path up towards the oil spill site. Here's the oil spill site. And then we decided we'd like to know what the currents are doing farther south, and we drove the glider down, and this has gone through an eddy that turned out to be there. The speeds are quite large. These are a couple knots here in the current, in the loop current, whereas near the spill they're quite weak, and so that the currents moving the oil around are really fairly weak. And we're pretty lucky in terms of us on the East Coast, in that the oil has been really localized. Again, here shows the vertical view, and you can see the large currents in the loop current. I mentioned that it had a acoustic backscatter, which is really measuring what kind of stuff is in the water. And this is a view of that data. And here again is the site of the oil spill. And it's hard to probably use it back. You can't see it, but I'll tell you it's really true. That there's we actually see some significant backscatter. Undoubtedly, we're pretty sure it's from oil drops at 400 to 500 meters down in the water column. So we can actually begin to see that there are indeed these appear to be these intermediate depth plumes in the ocean. That data from the gliders plus other data has been used to incorporate it into a computer model that makes predictions for what the currents are. I've shown you here 3 different snapshots of those analyses. First is the 4th of May, the 8th of June, and then the 16th of July. In the beginning, when the oil spill, the loop current was in its sort of more usual state, looping up like that. And then in early June, it actually formed an eddy, and then, as you can see, in July, the water is going into the Gulf Stream. Is really coming directly from the Caribbean. And it's been a little frustrating for me that people have been going on and on about worrying about the East Coast, because we're really not in jeopardy. And I've sort of been talking about this to people, but it seems to have been neglected. But the point is, the currents, the oil is really pretty much isolated up in the northern Gulf of Mexico, and we're not about to have oil swept into the North Atlantic, contrary to some things you might have read. So in conclusion, the first thing is that the loop current eddy is really shielding us from the oil. And one of the things that you'll hear from various people, that the oceanographic community has really done a great job of kind of rallying to help map out various things. In this case, we actually have 7 gliders working now in the Gulf of Mexico throughout the community, 4 on the shelf and 3 of us working in Deepwater. And our glider is being mapped out currents quite well. We see a 400-meter deep plume. And one of the things we should think about for the future is that gliders and other kinds of data like this can be used to form an ocean observing system that really is crucial for future, both for monitoring oil spills, for hurricane prediction, forecast for navigation, oil field operations. And in some sense, we can maybe take advantage of this opportunity to try to really evolve into a proper observing system for the Gulf of Mexico. Thank you.
Thank you, Breck. Way early in the oil spill, Breck was saying, I'm sure that there's going to be an eddy pinched off. I'm positive, but he was very careful about getting the data before he would confirm that. But he was predicting the future there, and he was quite optimistic that there would be a happy ending as far as the East Coast is concerned. And it's also a good example that the gliders, the deep technology that we have, and also that you don't have to be at the left-hand side of the table to be using technology to further the science that you're doing. I'd like to introduce Rich Camilli. Rich is a diver. He's an explorer. He's an inventor. He's a sculptor. He's also an MIT civil engineer. And what he likes to do is to take instruments and figure out how to put them down into the ocean so that they can do science for us. And I think you're going to see some examples of that. And these are technologies that were developed initially to support work for hydrothermal vents and for oil seeps. And so some of the basic science that's done here. And then with the oil spill, it became a very ready application. And I think you'll see that the results are quite interesting. So I'm going to introduce Rich Camilli.
I should start by saying I originally got involved with oil spill work after Hurricanes Katrina and Rita. At that time, after Rita in particular, there were approximately 150 oil platforms that were destroyed in the Gulf of Mexico. It didn't make the news at the time, or it didn't make the news much because of all of the damage that was sustained in New Orleans. But nonetheless, that provided an interesting entry into oil spill survey and cleanup activities. Since then, over the years, the past 5 years, I've been involved with other oil spills offshore, typically with downed platforms and broken pipelines. Now, with the Deepwater Horizon, I've been involved with 3 projects. The initial blowout preventer damage assessment, when the blowout initially happened, we were trying to figure out why it happened, why the blowout preventer failed to fully actuate. Then was involved with the U.S. Coast Guard to try and quantify that, the flow rate, the amount of oil and product coming out. That's an ongoing project. And most recently, I was involved with a NSF-funded research expedition on the RV Endeavor. It was called a RAPID program. And I think we did that in, I think, wrote the proposal in a matter of a couple of days, thanks to Judy Fenwick, and actually mobilized within a week. So it's very unusual, but this spill itself is unusual. It's unlike any down platform situation that I've ever seen, and part of that's because of the size. This right here provides a sense of scale. This is a CAD drawing of the blowout preventer, and 15,000 psi working pressure. It has a diameter, that's the throat of it, is 18 3/4 inches in diameter. This is the size of a water main. And in terms of its size, it's a third the length of the the Oceanus. Oceanus you sometimes see docked out here. And it's 5 times as heavy as a battle tank. So this isn't your garden variety blowout preventer. It's big, difficult to shut off. And so that was one of the problems. Another thing that's different about this is the depth. This well was sunk into an area where the seafloor depth is 1,500 meters. At that depth, you have what are called hydrates that form. I'm sure many of you have heard about these in the news. Hydrates were originally discovered by none other than Michael Faraday over a century ago. And this here is a structural model of hydrates. Basically, hydrates are, in this case, gas hydrates, are formed when natural gas causes ice to form at an elevated temperature. You could think of this as being like antifreeze working in reverse, where instead of making it so that water freezes at a lower temperature, water freezes at a higher temperature. And so you get ice formation in, for example, this containment dome that they tried initially. And that, by the way, is the standard procedure for dealing with spills of this nature. And anyway, at this depth, you can have hydrates form at almost room temperature. So it's a very different phenomena than what we're used to dealing with on the surface. This phenomena, by the way, also tends to happen in Arctic environments very easily, very near to the surface. And to give you a sense of what hydrates actually look like, this right here is a photograph that I took 4 years ago of something that's called the Sleeping Dragon hydrate formation. It's one of the biggest of its kind that's ever been found. This is 8 miles away from the Deepwater Horizon site. So hydrates are known to form there. And this background photo, it's difficult to see. This was during the cutting operations with when they were cutting the riser away. This plume you see here has hydrates forming in it, and it was actually forming around the ROVs, the remotely operated vehicles that were being used. So it's difficult to make observations in the subsurface environment, and that makes it difficult to answer very simple questions. How much oil is coming out? What kinds of chemicals are in the oil? Where is it going? And what will be the impacts? So I figured I'd take a couple of minutes here just to show some of the technologies that we're using on these projects. And one thing that I should point out is that many of these technologies were actually developed as a part of fundamental oceanographic research, but the technology is very transferable for use in these situations. This first photo here, this shows an acoustic system that we put together to help answer the question of how much oil is coming out. In this case, you see this is a manipulator arm on a big work-class remotely operated vehicle, big robot that was being used to try and stop the leak. And uses two systems here. This is a multi-beam imaging sonar. It makes the equivalent of grainy black and white images, but using sound beams instead of light. And then this system here is a Doppler acoustic velocity meter, and it uses sound waves and looks at the Doppler shift, the frequency shift, to tell how fast a fluid is moving. And so between the two, we can begin to put together the actual flow rate. So we took an ROV with these systems, used the imaging sonar to find the diameter of the plume, and then the Doppler system to calculate the velocity. And by multiplying the two, you can then establish the total flow rate. Then what we did, we went back after the top hat was put in place, and we used another system. It's a gas-tight water sampler that was developed by Jeff Seawald for sampling hydrothermal vent fluid. And in this case, instead of a hydrothermal vent, we used these samplers to actually poke inside the top hat and get oil samples so that we could ascertain how much of it was gas, how much of it was oil, and how much of it is what they sometimes call produced brine. So another technology that we've used is a in situ mass spectrometer. This is actually where I've spent a lot of my time working in the past 15 years, actually. This system can tell you what kinds of chemicals are in the oil. In this case, this is an in situ fingerprint that we did of a different blowout preventer, not too many miles away from the Deepwater horizon. In this case, we could identify what kinds of toxins were present, including things like benzene, toluene, and hydrogen sulfide. That's very important for cleanup efforts to know that these compounds are present. This, by the way, was done as a partnership through a program called the National Ocean Partnership Program, NOP, that seeks to use fundamental research work and transfer that into useful technologies, and did this in the development of Tethys in partnership with the company Monitor Instruments. Now, by taking that technology, we've also been able to use it on these big remotely operated vehicles. There you can see that guy's a little bit taller than me, and you see the size of that arm. That's the guy standing there. This is the vehicle. These things are huge. But we can go and take these and drive them around. In this case, this is yet another toppled platform. This one, by the way, when it was standing, it was taller than the Prudential building in Boston. Really big structures here. And we used this ROV and the mass spectrometer to drive around on the bottom and identify where the leaks were. This is a failed blowout preventer there, and also where the contamination was on the seafloor. Now, for the NSF program that we just undertook a few weeks ago, we used a different kind of AUV from what Breck had just described. This is the Sentry autonomous vehicle, and it's a little bit different in that it's bigger. It doesn't go as far as a glider, but it goes faster. And we used this as a forward reconnaissance tool so that we could basically have this robot swim surveys deep in the water column to look for traces of chemicals that provided targets that allowed us to vector in this ship and take samples using a process that's it's a federally mandated damage assessment, and that's useful for forensic type efforts that are ongoing. The neat thing about this was that for this cruise, it truly was a partnership between government, industry, and academics. We had, on the government side, we had NOAA, the EPA, and the Coast Guard with observers on the ship. We had academic partnerships with, in this case, the guy in this photo that you can't really see too well is Mike Jakuba. He's a former joint program student that's now at the Australian Center for Field Robotics. We also had observers from BP on the ship and a technician from Monitor Instruments, all working together so that we could find the samples in real time, or make the measurements in real time that would direct us to make better measurements and take better samples. So with that, I'll end. And James, I guess you're next.
Okay. Thanks, Rich. Appreciate that. I think you guys are getting the drift about the different technologies and how we can get them into the locations that we need to get them. We've seen gliders, big ROVs, and now we're going to hear a little bit more about the AUV that Rich talked about from James Kinsey. I've been here since March, and I just met James for the first time tonight. So he's at sea a lot. But I got to know him pretty well because the first week I was here, we lost the predecessor to the Sentry, the Abe, and James' name kept popping up on all the emails about what was happening and when it was happening, and I was looking at this as my first failure, the first week on the job. So I have a kinship with James, a Kinsey-ship. Anyhow, he's like Breck. He's a Johns Hopkins grad, and he's works in our deep submergence lab and really tries to get our vehicles to do the robotic things that we want them to do using navigation, control systems, and then making them so that they're able to help us apply the science needs. James?
Thanks. Oil spill experience. The whole robotics team here at Woods Hole, this is our first one. But a lot of the tools we've been developing for decades really came to bear. So I'm going to talk to you about some of the robotic technology we used on this cruise. I'm part of a really wonderful lab up here at Woods Hole, Deep Submergence Lab. It's been working on developing technology to work in the deep ocean for decades. We've developed the Jason ROV. We actually built a vehicle last year that can go to the full ocean depth near you. So we've always been looking to how can we build technology and take oceanography into the deep ocean depths. We don't do oil spills for a living. On this, when Rich came to us and said, we want to go and we want to take Tethys and we want to go deep, and we have a very important social interest, though, to go and study this very key problem, this really national, in some ways international disaster, we mobilized to the task. And I want to point out a couple key people, Dana Yorger at WHOI, Michael Jakuba. They're kind of my key partners in crime intellectually, the brain trust, so to speak, were involved with this. Also, this is the Sentry AUV. It doesn't run itself. There's a wonderful team of engineers who keep this going, and they deserve a lot of credit. Also, collaborations with Johns Hopkins University and the Australian Center for Field Robotics. So Rich came to us and said, here's the task. We have a cruise on Endeavour, a very short cruise. We don't have a lot of time, and we want to understand where is the oil, what type of oil is it, and what do we need to do? Well, we need to get a platform in the water with chemical sensors and start taking measurements. We also are going to be working on another program where we're going to be taking water samples, and those are going to go back to the laboratory for further analysis. Where do we take those samples? Two really key questions. This is our boat, the Endeavour. And the first thing you say, is what are the conventional methods? How would we do this conventionally? The first thing we'd do is what we call a CTD rosette. This is a conductivity temperature depth rosette. It's a frame. We've put sensors on it. These are actually plastic bottles that can take water samples. This is the bread and butter of oceanographic sampling. Every ship has one. You can take CTD ops all the time. And these bottles enter the water open at the ends, and you can close them. You can trigger them and take water samples. And this is attached to a wire, a very long wire, often thousands of meters. You can stop the ship. You can lower down the cage, take water samples as you come back up, put the CTD back on board, move to the next place, repeat. Sometimes you can even tow it behind the ship, but the ship has to move very slowly. So you're not covering a lot of ground fast. This is a very time-consuming process. So what are your other options? You can certainly go to oceanographic submersibles. Like Rich pointed out, he had done some very good work in the Gulf of Mexico with an ROV. Piloted vehicles like Alvin, like Jason. This is a tethered robot vehicle, just similar to what you're seeing at the blow-up preventer in the Gulf of Mexico. These vehicles can do a lot of good work, but they have to stay near a surface ship. In fact, the ROVs are attached to the surface ship by a tether. So they can't cover a lot of distance in a dive, less than 10 miles. Autonomous underwater vehicles, AUVs, this is Abe, this is Sentry, they can operate without human intervention, free of the ship. They can actually even go tens of miles or more in a single dive. So if you want to start covering ground fast, this is a great platform to do it. The trade-off, of course, with what Breck has is Breck's vehicle goes slower but gets better miles per gallon. It can go hundreds of miles, if not more, thousands. Ours, we're going to be under 100 miles. So and there's a lot of challenges in AUV technology, and we've been working on that in Woods Hole for almost 2 decades. And 3 really key ones are navigation, control, and mission planning. Big downside for us in navigation is GPS doesn't work in the water. What you have on your dashboard, it doesn't work. So we've had to spend quite a bit of effort in developing navigation techniques that do work in the water. And in fact, now we have the capability to know the position of our vehicles in tens of thousands of feet of water to within 15 feet. And if you think about it, that's a pretty impressive thing. Well, knowing where your is a good thing. There's also the control issue. There's no human. Our vehicles are always on autopilot. So you got to be able to place it be able to design a controller to place it where you need it. And we've actually been working on that on our ROVs, and that's mapped over to our autonomous underwater vehicles, and we can control those positions within a few feet in very deep ocean depths. Mission planning is probably the most interesting one. When we started in AUVs, we would just give the AUV a predefined set of tasks. Here's your hit list. Go down it. Go to this point, go to this point, go to this point. The much more interesting thing is having the vehicle decide how to do that on its own, saying, this is what I'm searching for. How can I autonomously decide where to go? And this is a picture of a methane cold seep, I believe, Rich, from off California from 2009. It was taken by the Sentry AUV. And there's an interesting story here. On this cruise, Rich was out on it, Chris Reddy was out on it. They put Rich's mass spec on it, and it was searching for methane. The ROV control system, the AUV's control system was taking those measurements, interpreting them, and deciding where to task the vehicle, taking photos as it went. This is a photograph it took at a place where it decided it had found a methane feature of interest. Up in the upper corner here, you're going to see a marker, a placard. That was left from an Alvin dive a few years earlier, where scientists in Alvin had been using the data they were seeing and said, let's leave a marker. This is a place that's interesting. This is where the AUV had decided this is what's interesting. And all of these technologies built into the navigation, the control, and finally the autonomy. How can I decide what to do? So these are really powerful platforms for ocean exploration. On this cruise, we were taking out the Sentry AUV. Sentry, again, it's an unmanned, untethered vehicle. Can go to 14,000 foot depth. It's a wing on edge, has 4 propellers, 2 on each side. These wings can help drive it up and down, kind of like an airplane, very similar to an airplane. Sentry and its predecessor, Abe, have been combined working all together for almost 2 decades. In fact, Sentry just finished dive 299 this evening. And none of this was done in context of oil spills. We've done seafloor mapping for geophysicists. We've done optical surveys of deep sea coral to better understand paleoceanography, climate change, hydrothermal vent exploration, looking for vents. All of this technology wasn't developed with the oil spill in mind, but when the time came, we were able to apply this knowledge to it. So even though we were taking tools we knew, this was a very different cruise. It was a very rapid cruise. We took the mass spectrometer and Sentry's autonomy, mobility, and precision nav, got it all on the vehicle. In 8 days, we did 7 dives. We covered over 200 miles. We're coordinating ops with the Sentry and the CTD. Sentry comes up, you look at information. Based on that information, in goes the CTD to collect water samples. Very rapid cycles. We mobilized very fast. You've been hearing tonight that the community responded very quickly. This is a 40-foot flatbed that left Woods Hole that was prepared in less than a week was down in Tampa 2 days later. They were bolting the vehicle together. We sailed 2 days after that. The entire crew cycle from beginning to end is less than a month. It's a very rapid operation. I don't show you this picture to say we get to see lots of nice sunsets at sea. When we operate in deep ocean science, typically you can go 4 or 5 week cruise without seeing a single ship. We like that in AUVs. If something goes wrong, the vehicle comes back to the surface. That's what we train it to do. That isn't an option here. We at times could count 50 vessels on the surface. ROV control ships, support ships that are a couple hundred feet in length, skimmer boats out here that have booms behind them that'll tangle anything on the surface. You've got burn-offs out here. This is a very challenging environment to work in. At this point, you have to have confidence in the autonomy of your vehicles. A number of times, we had to just leave the vehicle where it was and say, we trust the vehicle to do its mission, step sometimes to 10, 15 miles off site. We could do that, come back, the vehicle was still doing its job. At the end of the day, what really matters is the data. And you can see here a couple pictures from the lab. This is kind of the brain trust of the vehicle. We're looking at data. You can see Rich and Chris here looking at, you're kind of deciding what's the next step. And give you an idea of what this buys us. Over those 200 miles of track lines we covered, we collected over a million individual chemical sensor data points. That's an enormous amount of data that was collected. A very quick analysis of that was just used to say, let's put the CTD here, let's put it there. And of course, the next thing is, big step, the ongoing step now is the in-depth data analysis that is ongoing. And just a couple of key conclusions. The mass spec and Sentry are really a great and unique platform for doing it. They worked together well in the past. They work together here. And the data we have is going to be a very valuable source of understanding the extent and assessing the extent of this spill. And also that we were able to inform, really, the other operations on the ship. And finally, from a personal perspective, 3 months ago, if you had told me Sentry was going to go respond to an oil spill, I would have looked at you like you were crazy. I would have said, okay. But we were, in that time, able to take everything we had developed to fulfill this Oceanographics mission and apply it to a very crucial problem, and we were ready to when the time came. So with that, I'll hand it off to Chris, who's going to tell you a lot more about the science of what we do with the samples.
I think just to point out, the cruise that James was talking about was on the Endeavor, and it was a multidisciplinary cruise with our engineering capability, with biology, and with chemical oceanography aboard. It was four different rapids, or three different rapids. So 3 different sources of funds, all coming together. It was an entire WHOI production, other than the ship. So that we're really proud of what took place there and how fast it happened. I'd like to introduce Chris Reddy. Chris is an associate scientist. Let's get to in the chemistry and geochemistry department. And he's also the director of the Coastal Ocean Institute. He got his PhD in chemical oceanography from URI, and he has become one of the spokespersons for WHOI in this oil spill. We've done a lot of press activities. I'd say Chris has done half of them at least. He's very good at that, as I'm sure you'll see why in a second. But he's got an awful lot of oil spill experience, as listed down there, some of which started before he was born. He's also testified before Congress. He has regularly been asked to be on the radio and to be a spokesperson for us for this particular oil spill. Everybody's participated with the press, but Chris has done it, and he's done it very well. So, Chris, I'm going to turn it over to you.
So following these two guys, it's like they're like a laser beam, and I'm like a 40-watt light bulb in terms of the technology. They were bragging about their robots on the boat. I washed those plastic bottles with a toilet brush, and oh God, we all have our place. I'm going to talk about where the oil is going. Kind of simple forensics. Certainly, I'm just going to tease you. But I'm going to give you a little bit of insight about the spill, both from my personal perspective and give you a little feeling about the next time you read something in the New York Times, maybe whether or not how accurate it is, or maybe it's just provocative. I spend a lot of time on oil spills, whether they happened 40 years ago. There's an oil spill every day off the coast of Santa Barbara. I spend a lot of time in Santa Barbara. other places as well. I get used to it. I know oil spills. When you're on site in an oil spill, the first thing you see is that the oil is damp in the sea surface. So you see the sea surface kind of quiet, and then you kind of see the sheen. And then if the wind blows, you start to see the oil, the smell of the oil. And so that's usually my experience. And then if you go to spills after the fact, you got to look a little bit harder. This oil spill that happened in 1969, you got to look about 3 or 4 inches below the surface. An oil spill a year later in San Francisco Bay, you got to scrape, and then you find the oil. It's an important concept that just the sheer fact that you can't see it doesn't mean the oil's gone. Sometimes you got to look a little hard for it, but the question is whether or not, when you're looking that hard for it, does it actually mean anything? And these are things that we have to keep in mind. The sheer fact that you can see oil doesn't necessarily mean it's a bad thing. And these will be discussions that will be in the New York Times frequently, probably in the future. This is what happened to us when we were on site. We're not too far away from the spills, the broken riser pipe. We had another sense, the sound. Those are the 2 jets that were burning off oil that they had this little top hat that Rich was showing. There were 2 boats, the Discover Enterprise and the Q4000. That sound was constantly running in the background. And it added a new level to our senses that we work with. We often had to have earplugs in our ears. Rich talked a little bit about how we had to collect a real sample from the broken riser pipe. So we took the remotely operated vehicle and we lowered it down with a special sampler and we collected a sample. When we did that, we were taken over off the Endeavor to another boat on a fast boat, picked us up onto a very large boat, 5 stories up in the air. We went into a conference room for about 3 or 4 hours. When we got into the conference room, we were about 3 or 4 miles off site. We talked about the plans, about how we were going to collect this special sample. And then we got back on the deck. We had another sense that overwhelmed us. It was our skin. This is what happened. We were right in between those 2 flames. One flame, the other flame. We were basically right over the broken pipe. That was the vehicle that we were adding our special sampler on so that we could get a sample of oil. Couldn't hear. You see in a lot of the pictures, you see these badges. These are badges that we were wearing for air quality testing. So we had also a professional air quality health scientist on our crews to keep an eye on us. Again, if you stood, this is after the boat on the port side, if you stood that close over there, you would feel the heat on your skin. So there was just another aspect of this. I mean, people use unprecedented, but it's actually a quite accurate term in so many levels. I took that video with my BlackBerry, which... So people are very confused about oil spill science and who does what and why isn't this being done and where's this going, and this is very confusing. It has to do with a concept of federal mandate. There's a federal mandate for 2 aspects of oil spills. They have to respond to the spill. The Coast Guard, NOAA, other government officials, and what they call the responsible party. That's an oil spill, that's the person who did the problem. They spilled the milk. They don't say BP, it's actually, you'll hear RP, the responsible party. They're responsible for booming, skimming the oil, fixing the problem. That's called the response. Okay. They're also responsible to try to figure out kind of the concept, if the responsible party breaks it, they got to buy it. This came after the Oil Pollution Act of 1990. So it's called the damage assessment and restoration. What was damaged? How can we fix it? There's science involved in that as well. So you have 2 circles. In the middle, there's a lot of science that doesn't get picked up due to these federal mandates. Some of it gets picked up. In this case of the spill, because it's so unusual, a lot was going to get missed. And we're very lucky that the National Science Foundation and other organizations recognized that there was an importance to fill in the gap. Most oil spills, this middle part actually is kind of lost. We, on our Endeavor cruise, actually were able to hit all three circles. We, on our cruise, we called in many times a day to say, oh, we see a lot of oil over here. And then they could vector in skimmers. We also helped out in this damage assessment. Here's the deal about damage assessment. You got to figure out the concentration of your oil in the water. And then you also have to figure out how long something's been exposed. It's called concentration and duration. How these guys helped me, I'm the guy who cares about oil in the water, is they helped me find the oil. Because otherwise, when you try to sample for water in this area, you basically are taking the package or the rosette that James talked about, and you're poking. And you're hoping you find water that has oil in it so that you can help out and figure out where the oil was and then make a fair assessment that this much oil in this area may have caused a problem. You might be able to find it without their help. But you have to collect these samples. They're incredibly precious. It costs thousands of dollars to analyze them. But more importantly, they only have a shelf life of 7 days. So when we collected these samples, not only did we have to collect them, archive them, we had EPA, NOAA, and British Petroleum watching us tape the bottle shut. Then every 3 days, we had another boat come pick up the samples, making sure they stay at 4 degrees Celsius, so a little less than 40 degrees Fahrenheit, and ship them off. That's why it was so important to have these guys with us. They helped me save so much time and confidence to say, if I was going to collect a water sample, I'd go right there. And that's what I had, and not many other groups did. We're still working on analyzing that data. It takes a long time to analyze oil in a much more comprehensive way than what Rich's package can do. We're working on that, and some other day we'll talk about it. I'm going to talk a little bit about this question of where did the oil go? It's in the newspaper all the time. Then later on, I'm going to talk about how when they say, oh, they found some oil in Florida, but it didn't come from that spill. It's not from the Deepwater Horizon. It came from something else. So I'm going to talk about two things. This is kind of the research that I do in some cases. Okay, we've been talking about oil all night. Nobody said what oil is. So it's old plant debris, algae in most cases, that over hundreds of millions of years is cooked and squeezed. You cook and squeeze old plant debris. Think of your compost pile. And if you cooked and squeezed it enough, you would make black gold for oil, crude oil. Okay, we tap it. That's crude oil. Okay, that is it. Now, crude oil as itself, does anybody use crude oil straight? No. We refine it because we want to take advantage of the different chemicals that make up crude oil that have use. We take out chemicals that are in the gasoline range to drive our cars. We take out some other chemicals that have properties or personalities to make plastic, other properties to heat our home. Okay? Those different chemical properties or personalities, I exploit as an oil spill scientist. I say, oh, that chemical right there, it likes to evaporate more than that chemical. And that allows me to disentangle all the different processes that may act on when oil gets spilled and be able to tell people there's been a lot of evaporation in this spot versus another location. So I like to look at chemicals and try to get a feeling for what goes on. I live in the world of a big jigsaw puzzle of molecules, and I'm constantly trying to do that. And at the end of the day, I try to rectify the checkbook of oil that's been spilled and try to figure out where everybody went and how it went and how fast it went. Okay, I'm just going to talk about two samples. We collect a lot of samples. My lab's got hundreds of samples, but I'm just going to talk about two real, what we call real-world samples. This is a sample that we collected about a mile away from where the broken riser pipe was. And we collected this brown oil. And this is what the oil looks like on the surface. It looks like Swiss Miss cocoa. I mean, it's not this black oil that you think about. It's brown. And we collected some of that. And I'm going to show you some analyses of that oil. So this is oil that went up 5,000 feet, went over about a mile. Okay. This is another sample of oil. Judy showed you a figure from USA Today early on. And if you could go as far left as possible and far, well, let's go far west and far north. Let's be an oceanographer. This is where I collected this sample. So as far away as possible. This is a little tiny marsh, a little island that's got a marshland there. And you can see that this brown kind of, this is about 3 feet thick, 3 feet wide, a painting of oil. What's interesting about this site is that if you walked around, there wasn't any other oil on this little island. It's because oil kind of works in kind of patches. And you can almost think about this location got hit with a big syringe of oil right there. So I collected some oil there. Okay, so now I'm going to show you data from a sample that went 5 miles up, 1 mile over, 5 miles up, 50 miles over. I'm going to talk about how those different chemicals have different personalities, how they may have changed through time. Oil is not one single entity, right? Many, many different molecules. We were lucky to get some oil via British Petroleum, of the oil that came from the reservoir before they had this disaster. This is a map of the oil. Think about each one of those little spots is kind of like a mountain, okay? And the bigger the peak, in this case, the kind of more enriched it looks, it's more abundant, okay? So when I look at these maps, not only can I tell who's there by where their placement is in kind of the northwest and help me out here, up and down, left and right. When I look at this, I'm lucky. I can see, oh, that's a chemical that likes to do this. Chemicals in this region like to evaporate. The chemicals in this region are particularly tough. Tough means that nature can't really do much with them. And I'm going to talk about the chemicals that aren't so tough and some of the chemicals that are tough and how we can use them to tell a story. Okay? We've also analyzed that oil from collecting it with that device earlier. It looks exactly the same, which is encouraging on many cases. So, okay, this is what came out of the riser pipe. I'm going to show you what it looks like when you go on a 5,000-foot ride up and a 1-mile ride over. Remember, this is a map of all the different compounds. This is our inventory, our warehouse of compounds. 1 mile over. Something happened. We lost a lot of compounds. Okay? We lost a lot on the far left. That's 1 mile over. I'm going to show you the next sample. This went on a 50-mile ride after it surfaced. Oil is changing. The composition of oil is not the same as it came out of the riser pipe. It's important to know that because that means that a lot of different properties, the capacity to skim it, the capacity to burn it, its capacity to inflict biological problems, all are constantly changing due to these personalities of different chemicals that make up the oil. Let's go back to the original oil. 50 miles. This was taken on Memorial Day. This is what came out. Amazing difference. Well, what happened? Well, that 1 mile away, when I look at that and I do a little math, that area where we lost all that signal, we bulldoze away those mountains of compounds. That's a region where compounds are most likely to evaporate. So I can sit down and I'm going to start doing some math soon and say X% of the oil was evaporating in this region. Okay? Let's talk about that other oil that went 50 miles away. It had another process acting on it. It evaporated and even had more stuff in that box moved over. More material was evaporated. But something else happened. Those blades of oil were enrobed with oil. And when those blades of grass were enrobed with oil. I went and scraped some off. And then every day before that spill, when that landed, I'm not quite sure when it hit, but then thereafter, the tide came in and out. Okay? The concept that oil and water don't mix is not actually true. There are some compounds that have a slight affinity to dissolve in water. And so every day you've got this oil enrobing this grass, and the tide comes in and the tide comes out. Tide comes in, tide comes out. What does it do? It washes away some of those compounds who have a slight affinity for water. And we call it water washing. And that region right there is what I think got water washed. It's an important process because that brings compounds that were sitting on the blades of grass back into the water where it could potentially expose wildlife. So trying to disentangle regions where a compound could have evaporated, which is usually pretty benign, or washed is really important. And it just so happens that this area right here is where a lot of the compounds of concern in terms of from a biological activity exist. So it's really important, and one of the high points of my efforts for the next year or so is to figure out compounds right here. Do they go up or do they wash out? Okay. I'm doing this for you. This is, I feel a little like the Karate Kid because I got a lot of senseis in the audience. It's really not fair for me. This guy, this guy, this guy. Jeez, my mom and dad be here. They're the only other problem. When I was showing you those pictures back there were some compounds that didn't change. They don't mind. They don't evaporate. They don't water wash. Sunlight can't do anything. They are tough. Okay? They're called, we use these compounds. They're really quite effective compounds. In our world, they're called molecular fossils. Molecules that are fossils. They're tough. And that's why they're fossils, because they can last for a while. So, how do I use those fossils? You hear this in the newspaper. Oh, there's a tar ball, Pensacola. Nope, didn't come from the Deepwater Horizon. I'm going to tell you why they say that. And this is a particularly difficult challenge to try to figure out if a tar ball came from a certain place in Louisiana, in the Gulf of Mexico, because you have a lot of places where oil could come from. You have the Deepwater Horizon accident. You have 40 million gallons a year of natural oil seeps coming into the Gulf. You have previous accidents. You have the oil that seeped out from the hurricanes. This is a place where you've got a lot of, let's say, genetic. This oil spill, all the oil in the region is a lot of cousins. Okay, most oil spills, when we try to disentangle and there's a problem, it's like a long, long lost cousin, and you say, that's the oil that spilled in Buzzards Bay. I can tell it's because it's got this signature. The Gulf of Mexico is a particularly challenging place to do this. And we approach it by taking advantage of some fossils. Now, everybody thinks about a fossil and they think of a bone. Okay? We think about it as a structure. Okay? So this dinosaur had a hip bone, and it persisted. In fact, it actually broke. But actually, a paleontologist is like, that's okay. It changed a little, but it still helps me tell a story. Well, this is a bacteria that may have helped convert that old algae in that compost pile and make it into oil. Okay? And it used a compound that was a little bit different than what this structure is here. But it's okay, because we can tie it all back, just like a paleontologist can put the two broken bones. These compounds are called hopanes. Okay? We use these compounds to tell who comes from where. I'm going to show you some maps again. But instead of showing them what you call plan view, I'm going to show you some mountain plots to kind of pull out some of these differences. Don't worry about the structures. Don't worry about anything. Just enjoy the fact that something goes up and something goes down. Okay. Okay, I'm going to show you 3 pictures from the most 3 iconic spills in United States history. Deepwater Horizon, Exxon Valdez oil, an oil that was probably very similar to the Santa Barbara oil spill from the 60s. Okay? Can we dim the lights? How are we doing? Can we do it? I'm not trying to be dramatic. It just will help you guys out a little. Okay, that's cool. Oh, thanks, Judy. Okay, so. Cool. All right. So this is kind of, think of this as another map, okay? And Bob Nelson, who's back up there, he's the wonder guy. I'm like Martha Stewart on the TV show. I don't do anything. I just look like I do. All scientists do. It's the other people who do the work. I just get to talk. And this is very important, especially in this case of the spill. For every one scientist who's talking about their work, there's a support staff of 5, 10 people. The institution has had a lot of people involved, and as well as other places as too. So just look at my friend with the capital H, and then maybe a little bit over to the left you see BNH. So H is hopane, and BNH is a compound called bisnorhopane. Okay, so this is what seeped out from Deepwater Horizon. Okay. Just watch these changes with BNH. And actually, let's throw in NH. We'll make it complicated. 3 peaks. BNH, NH, this. Look at the relative proportions. Okay, this is what came out of the Gulf of Mexico. This is Exxon Valdez. So Exxon Valdez is very different. Has a lot more norhopane at NH than what came out. There's a lot of reasons, a lot of other people who can explain that better than me, but I take advantage of these molecules to help me tell a story. Let's talk about what comes out of Santa Barbara. And this came from a platform that's about 2 miles off the coast of University of California, Santa Barbara. Look at bisnorhopane in this sample, BNH. This is what probably spilled out very similar in 1960s in the Santa Barbara oil spill. Bisnorhopane just blows out the signal. You're going to start to get a feel about how just to trace, these compounds make just a trace amount of the original oil. But as time goes on, they're so tough that they stick around. They don't break down. They're big, they're clunky, their shape makes them allow to hang out for a long time, and they hang out and they end up being the very powerful chemicals. I'm just going to tie up with just a couple more slides. So we have our 3 iconic spills. I got you believing that the images can be different, which means that the oils have different genetic makeup. Okay, here's a Deepwater crude. Okay, next sample is what happened. We found 1 mile away. So it's just about the same. It's all the relative heights are going on. This instrument kind of is just a little bit jumpy. But if we looked at these heights in relative amounts, the crude, what happened 1 mile away, what happened 50 miles away, the genetic makeup is the same. It's good. So these are compounds that are tough. All those other ones evaporated, water washed, they don't. All right, let's talk about potentially other samples that people may find and say, oh, I found an oil particle. Well, you might have some other crude oil. This is a crude that I have from 1970s. Okay, the difference between this is an oil that came from the Gulf of Mexico, and look at its difference. Look at norhopane, NH. So it's from the Gulf of Mexico. It was pulled up from a drilling rig, used, sold, but yet even in the same place, it can have a potentially different signature. Now I told you about these natural oil seeps where oil comes up naturally from the ground. This is what the signature looks like for the natural seeps. This is off from the it has a very different signature as well. So with all this data together, we'll start telling a story about who came from what. That's kind of fun. It's kind of like stamp collecting. But there's a really more important science aspect of doing that, which is when I can find an oil particle, and I can say genetically that it came from Deepwater Horizon, and it traveled 120 miles, then it has a history. and I can look at that history, and I can see what molecules are still there, and I can say, that 3 years later, 120 miles, I know it's this oil, so now what's left allows me to start telling a much richer and deeper story with confidence. So I think, just in summary, we have a lot of work on the way, and we're also working towards some really exciting environmental forensics. So I think we're done.
Okay, time for questions. If we can use the mics, and if we have enough folks line up behind. And if you wouldn't mind identifying yourself, that'd be great.
Hi, this is David Dow. One of the things that's unique about the BP oil spill is that they've used a lot of dispersants out in the open ocean to increase microbial breakdown and also to dilute the oil, and that results in impacts in the ocean, and also when this oil arrives on shore, it's in a more weathered state. I was wondering if you could comment on the effects of the dispersants and what might happen both in the wetlands and out in the ocean to the biota. Thanks.
Thank you. Chris, do you want to take that?
Sure. First thing you have to remember is that there's a unified command down in Louisiana that makes decisions about, in the response phase, which I spoke about earlier. And they have to make decisions, and often they're not very easy to make. Think about two firefighters who just come up to a car accident, and they have to do some trauma and some triage problems immediately. And then you have to try to figure out how to help this patient. The people down at the Joint Command, and this includes British Petroleum representatives, United States Coast Guard, NOAA, they have to make a decision sometimes about what they're going to use. These decisions are all wrapped around two words: reduce damages. So, when they use dispersants, the overall thought is, we're going to use dispersants because we believe it's a better option than not doing it alone. The people who make those decisions have been working on oil spills for all the oil spills that have happened since Exxon Valdez. So decision makers in using dispersants in the surface of the ocean, I have great faith in using them. It's a trade-off. They say, if I don't disperse it, it's more likely oil is going to hit the coastline and potentially make a bigger impact. If I do disperse it, I may release more. I'm adding more chemicals to the environment, and I may be able to, we may increase exposure. It's a trade-off. The people who make those decisions in the surface to make them, I'd follow their lead. They write the papers. There's a stack of literature this high about dispersants in the surface ocean. With that said, using dispersants below the subsurface, there's no papers about it. The people who decided to use them are the same people. So they have good experience, but they have no scientific data. Whether that was a good idea, we'll have to see. At this point, I'm not quite sure whether that was a good idea to disperse oil or not. Let's let the data play that out. But it's a trade-off. It's nothing easy in responding to oil spills of this size.
Just as a follow-up, would you guys that were there at the site, do you think it would have been a different site from a habitability standpoint, with or without the dispersant?
I'm not going to comment, but I'll show you a dispersant. See this? This is part of the dispersant right here. So we could see them when they were using them, but it's not easy. There's no easy decisions in oil spills.
I've worked on the toxicity of dispersants, and both naturally dispersed and oil-dispersed oil. And certainly the dispersants, their whole property is to break the oil into smaller droplets and to emulsify it. And Cabell Davis is out in the Gulf of Mexico now. He does see measuring the size of oil droplets below the surface. I certainly think that dispersants, have contributed to spreading the oil in a broader geographical scope. But I agree with Chris, both from a human health perspective as well as an ecological perspective. Without dispersants, more oil would have come to sea, and the workers on the ships would have been impacted much greater if they didn't try to disperse the oil. The dispersants used in spills in the 1960s were basically, oftentimes they used, gallons of detergent, and there'd be as many gallons of detergent as there were gallons of oil. The dispersants used today are much more concentrated, and they're used 1 part dispersant to 100 parts of oil. They do have a toxic effect. There's no doubt about that. But when you're, as Chris said, when you're weighing the risks of human health impacts and ecological damage, sometimes you need to use dispersants, and you need to use them carefully. The deep injection of dispersants, I think, is a wide open question, and it remains to be seen, what impacts we're going to see in those mid-water habitats where dispersants were used at depth.
You have a question over there?
Yeah, my name's Tom Novak. Regarding the loop current and the eddy, with the eddy keeping the oil out of the Gulf Stream or wherever, what's your timetable for the eddy breakdown and the normal loop current taking over and maybe bringing some of the oil into the ocean, the main ocean?
The loop current's going to very slowly migrate to the west, so it'll be there for another month or so. And I think, in some sense, the eddy also acts to keep the loop current from coming up. And so I think if you look at history, it'll be a month or two before, at the earliest, before it would do something. So I think we're safe in the short term. And I think, we have the advantage that oil is, it's turned off, it's weathering, so we don't have that same slick that we would have had otherwise.
Sir.
My name's Scott Smith, and I'm from Cape Cod. I actually have been down in the Gulf and had approval to the Robert, Louisiana Command Center, and I've been summoned to Dalian, China by the Chinese. I have pictures posted on YouTube. I'm based on Cape Cod. My company was almost wiped out in a flood in 2006 with oil-contaminated water. I have a foam that's been approved by BP. I've been approved for the Mobile Command Center. It's 70% less weight than the conventional booms. And my question revolves around conventional white sorbents and booms and dispersants. But I want to explain a few things first. I've been on the water with the fishermen. I've been in the Tyvek suits, been in the 120-degree heat. And I didn't realize until I got, and I watched everyone on the national news. I haven't been on the national news at this point, and that's not why I did this. With just ideas. I had a product, and I went there for environmental reasons to prove that it worked. So I chartered a boat, went into the Gulf, made a video on my iPhone. The captain that I chartered the boat was a local fisherman, said 57,000 people before you. And I've got a joke with the BP people, though, that I'm not a whack job. It's kind of humorous. But anyway, I went into a marsh, cleaned the oil, sent a video off to Plaquemines Parish, got a call from BP. They looked at the video. I was approved for the Robert, Louisiana Unified Command Center, went there, went to Mobile, and I'm told this is the first new sorbent approved in over 30 years. And what I've learned, there's a huge difference between adsorption and absorption, and it's all about surface area. I've been, again, out on the water with the people doing the work. I've seen sinking booms, I've seen waterlogged booms, I've seen booms going to dumps. This product can be reused up to 100 times. It can be wrung out. It can be centrifuged. And it really works. And we actually have an underwater oil plume detection system where we put sinkers on it. And I've been in the plumes in Fort Walton Beach. I've been off Fairhope, Alabama. I've been in Venice. I stayed at the fishermen's houses when I was there. And it's interesting, the people that do the work started calling this green stuff, and I didn't realize in the heat what a big deal it is. It's 80% less in weight. It actually absorbs. So the oil goes into this.
Scott, can I ask you to
It doesn't come out.
come to a question?
Yeah, the question is, the existing booms and the absorbance and the surface area, does that come up about that they're not picking up oil and the oil comes off in the water? And what is and the dispersants? Is it true that the dispersants are kerosene based?
Well, first of all, there's a number of different solvents that are used. The more modern dispersants are not kerosene based, but they are an organic solvent base. It's how it breaks up the oil droplets. And I'll defer the boom technology to Chris, who's experienced more boom deployment. But certainly more innovative techniques for controlling the surface slicks are definitely needed. And I think one of the things that we've noted throughout many of the spills is that how poorly prepared communities are to deal with these spills. So if your materials were available in Louisiana April 22nd, you could have avoided many of the problems that they have faced. And communities aren't prepared, even though all the recommendations are to make sure that the industry is prepared for accidents like this. So, Chris, do you want to comment on the booms?
Two things. One is that I get 20 phone calls a day about new technologies, whether they're absorbent-based or microbial. It sounds like yours is working, so I'm happy for you. One of the reasons why nothing's really happened in the last 20 years is that we've been a victim of our own success. Exxon Valdez spilled 11 million gallons in 1989. We had an oil spill for 1 million gallons in 1991. There was not an oil spill larger than 1 million gallons since 1991. Things got good because of laws passed, because Exxon sold all their tankers, practically, because they didn't want a bad business. GPS, good charts, cell phones, all this together led to us having very good oil spill prevention, which slowed down oil spill science, which slowed down oil spill cleanup. So there's a big thing going on here. To be honest with you, I was at every player in this oil spill, kind of the chemist aspect. We were all at the University of New Hampshire last year. You know what we talked about? We didn't talk about a Gulf of Mexico spill. We all talked about a spill of a new biofuel or a spill in the Arctic, because the Arctic is opening up due to climate change. Nobody talked about the Gulf of Mexico. Nobody talked about a Deepwater spill. So,
thanks. Next question.
I'm Megan Shea, and I'm here with the SEA Summer High School program. And you mentioned that there's already naturally occurring oil seeps in the Gulf. To what level, if any, will this minimize the effects of the spill?
I don't think that the presence of natural oil seeps is going to affect the long-term impact of the spill or anything like that. What you may want to think about is when people talk about natural oil seeps in the Gulf of Mexico is that 40 million gallons spills a year. Let's make believe there's 400 days in a year. That's 100,000 gallons a day that spills over a very large area. Oil seeps are like little black droplets spread all over areas, and then we have this big gusher. So natural oil seeps do contribute to oil in the Gulf of Mexico, but they're very discreet, and they're like a leaky faucet. And they spill a lot less on a total basis relative than what's happened in the Gulf of Mexico. I do not think the presence of natural oil seeps is going to make a difference in the long-term impacts of a Gulf spill.
Where natural seeps occur, there are communities of organisms that have evolved over time to adapt to that habitat. So you'll certainly find, a higher degree of microbial degrading microbes. You'll find, other organisms who are happy to live in those oil seeps because they use the oil as a carbon source. There's been speculation that maybe the Gulf of Mexico is more triggered to explode with these adaptive organisms. That's an interesting question. I don't think anybody has demonstrated that, but certainly the seep communities are isolated, and you do have rich communities being supported by those natural seeps, living communities. Whether or not that influences the rest of the Gulf of ecosystem, I think, is a stretch, but there still might be some interesting accommodation in some regions of the Gulf, and that's a great question that we need to address.
John, can I just put you off for a sec? We'd had some questions that we got from the internet, and I wanted to be sure we got to one or two of them. And so this was from Sarah Zero from Berlin, and we got some from Ireland, California. But anyhow, the question here was, what does the seafloor in the area of the spill look like, and how much of the oil is sinking to the ground? And what about cold water corals and cold seeps and their associated fauna that were found in the area before the accidents? Are there death zones now?
Well, I guess I could start by saying generally in the area where the well was being drilled, it's typical of the deep slope area, a lot of fine sediments, and not like a coral reef like you would see like the Great Barrier Reef or something like that. There are deep corals in the areas around there. One in particular is called Lophelia. It's sort of an enigmatic coral because it grows deep and it appears to grow very, very slowly. Not much is known about it, and there are cold seep communities nearby there. Just to the northwest, there's an area that's the Mississippi Canyon 118 site that actually that's where that Sleeping Dragon formation is, and there are other cold seep sites to the west. Those cold seep sites, that's where basically the earth is cracked, and the hydrocarbons seep up through the seafloor and actually go and make hydrates, but the microbes tend to eat the methane and other lighter hydrocarbons and convert it over into carbonate. So they actually change it into a carbonate rock. And one of the interesting things that happens with cold seeps that's it's not really that well understood. It appears as though the microbes themselves sort of cause these cracks in the earth to seal up, self-healing, like a self-healing tire, and eventually clog up the leak. So generally speaking, the natural seeps, like Chris said, tend to be very small and have just a little amounts of oil and gas coming out.
Thank you. I think I mentioned that we've put some sediment traps out, and the mastermind of the sediment traps, I see him back there, Chris German. And so those will be some of the techniques we'll use to try to analyze what the conditions will be and what the effects will be on the seafloor in the vicinity of the spill. Okay, John, thanks for being patient.
No problem. This is really great, what you've done. One thing that I'm reminded of is something that Judy and I wrote several years ago, and we weren't the only ones, and there's been some recent press on it too. And I was reminded by Chris's comment that indeed in the United States we've been relatively lucky. Other areas of the world is not the case, especially in developing countries. And that's one of the places, for example, where the gentleman with all of the sorbents and so forth, there's big need in these areas, like Nigeria, for example, where you have huge amounts of oil coming in from almost daily spills because they don't have the regulatory backup that they need.
Thank you, John. Next question.
Thank you. Chris Latazzi, WHOI Summer Student Fellow. My question is for Dr. McDowell. I was wondering what your thoughts were for burning marshes as a possible remedy to this solution.
Well, if you looked at some of the recent studies in the Louisiana marshes that were heavily oiled, that oil has evaporated or been degraded. And experimental studies in Louisiana from both experimental oiling as well as pipeline bursts, and now what we're seeing from marshes that have been oiled from the Deep Horizon spill, is that they are recovering very quickly. In some of the experimental studies, the marshes responded within 3 months. And so, to me, the burning the marshes right now would be that, a physical degradation that maybe isn't needed at this point because of the high rate of microbial degradation and the high rate of evaporation, because this has occurred over the summertime. Now, other marshes, George Hampson could certainly speak to that from some of the marshes in Falmouth that were contaminated. There was a marsh in Chile that was impacted by an oil spill. It took over 20 years to recover. So, the situation we have now in the Gulf is for the marsh habitats themselves, it looks like natural processes are improving the situation rapidly.
Thank you.
Next question.
My name is Lorraine Mahoney. I'm not a scientist or a student, but I've been reading that microbes, when they eat oil, create dead zones. Do we have dead zones in the Gulf, and how long does it take to get rid of a dead zone?
That's a really complicated question because microbes certainly use oxygen, and there have been dead zones described in the Mississippi, but they're more related to the stratification of the water column in the summertime with the high nutrient loads coming down the Mississippi River. I think right now there's certainly, another colleague who's not here on the panel was studying some of the microbial communities in the water column along with these guys. They can speak better to his results. But I don't think that he found dead zones. Dead zones, certainly we have hypoxia or low oxygen, and even sometimes anoxia, no oxygen in Wacoit Bay, especially in hot summer months when there's high productivity. That's what really causes a dead zone, if you want to call it that. It's more low oxygen rather than no oxygen.
And if I can add one thing, there's a fair amount of interest scientifically in this question, not only from the biological standpoint, but also from a sensory standpoint for us gearheads, because some of the sensors that are used to measure the oxygen concentration in water also exhibit a cross-sensitivity to oil. So if you expose them to oil, they can give a signal that masquerades as a low oxygen signal, but is in fact caused by the oil fouling of the instrument itself. So it's being looked into. But there is a technique, it's called a Winkler titration method. It was developed in 1888. That it's a little bit labor intensive, but it's probably the best thing you can do when making those measurements.
Thanks. Sir?
John Hayes, I'm a WHOI alum. I wonder what anybody can say about the amounts and fates of oil in the water column, not on the top, not on the bottom, but dissolved or suspended. One hears about plumes, and we don't hear much about how much and what's happening.
Do you want to go? There is, in the newspapers and reported by some of my colleagues, evidence of plumes in the subsurface. Their results are based on thinking about taking the Gulf of Mexico and just kind of stabbing it in a few places. And I'm not saying that it was arbitrarily, but they're stabbing it and seeing some oil in there. And it's difficult to constrain. Think about, just trying to solve a crossword puzzle with just a few pieces. That's where we are right now. So, but what's happening is the data, a lot of samples have been collected below the surface. And every day that data gets uploaded on a website, and I get to see it, and the pictures getting filled in. And I suspect probably in a couple, 2 or 3 months, we'll be able to see kind of in a 3-dimensional space where the oil was, and then think of it as a big long pipe, and what we would say integrate the amount of oil in there to get an idea as to how much was in there. And then maybe perhaps even see what type of the oil was right near the wellhead, and then kind of follow this pipe in one direction and see how the oil changed over time. It is a question that the reason why I went on that cruise was mainly to answer that question. Oil on the surface is not new. I mean, it's important, but trying to figure out what happens when nature gets an uninvited guest and doesn't bring it to the surface, but traps it in between. And that's one of the big science questions of this spill.
What percentage do you think is in the water column as opposed to on top?
Can I write you an email, John, in a couple months? I think being a scientist, this is a really important point that's been going on with my scientific brethren, news, agencies. We have to balance being scientifically prudent with trying to urgency. And there are times when we need to give data because the urgency is such that we have to make a decision about whether to boom or to burn. There are other cases where it's much more prudent to say, well, you know what? There's really nothing you can do. I'm going to tell you, I honestly believe that there's oil at 3,000 feet below the surface. It would be more difficult to clean that up than it is to cap the well. So it's much more prudent to wait it out, collect as much data, have colleagues work together on a team without any pressure to be able to get an idea as to answer John's question. So it's not like we're punting right now. It's prudence. Good scientists are prudent. And they're skeptics.
One thing, John Farrington, maybe you can chime in here. Going back to the Ixtoc blowout, which happened in 1979, based on John's report that I read, that he graciously sent a copy of.
He had 4 copies of
Yeah,
both.
yeah. If I did my back-of-the-envelope calculations right, that blowout, which was in 50 meters of water, keep in mind, the Deepwater horizon is 30 times deeper. But at the Ixtoc blowout, in only 50 meters of water, there were benzene plumes that advected 40 kilometers downrange, so roughly 25 miles downrange in 150 feet of water. So, and these weren't faint plumes; they were pretty strong. So we're now in water that's 30 times deeper. It's likely that there are plumes down there. We hope to be able to comment more on that soon. But there's a wealth of literature out there that suggests that plumes can not only form in the water column, but some of them can become trapped and persist in the water column. And so that raises these other questions of exposure and duration for benthic organisms and also long-range transport.
Thanks. Sir?
This is a very non-technical question. Did you find that the contentious relationship between BP and parts of the federal government was a problem for your work? And you don't have to answer that. I think you have answered it. And the question...
I will answer that question. When the interactions with, for example, for the British Petroleum representative of our boat, he was part of our team and he played an important role in helping us collect samples. If you speak to the people, the boots on the ground, representatives with BP, the boots on the ground with NOAA and the Coast Guard, they have a lot of respect for each of them because they all collectively want to reduce damages.
Right.
Up levels, that's out of my pay grade. But I will tell you, people who care about the spill, the people that that BP works for that are much closer to trying to reduce damages, I think they were doing a good job. Up levels and PR and spin masters, that's not my world.
Right. One more question. How many of you are writing a book?
I think back to your first part of your question, it's important to point out that BP facilitated a lot of the work that we did around the site, and the only way that would have happened would have been to provide the platforms that we worked from and the ROVs that we put our tools on.
I have to say that, generally speaking, the interactions that I, for example, had was mostly with contractors that are working there hired on behalf of BP. Like, for example, Oceaneering. These guys were fantastic. They were like an Indianapolis pit crew when we were taking those samples. They were literally rebuilding those big robots right on the ships. At one point, when we were working there, one of the robots, one of those massive manipulator arms snapped on the robot, and they had to rebuild it right there. And it was a pleasure to watch. It was pretty amazing. So there are a lot of very motivated people down there. And like Chris said, the people that are down there working, they have a job to do. A lot of the people come from Louisiana. And so their lives, their families' lives are being impacted. So they're working hard.
Any more questions? I guess before we close, I'd like to be sure to acknowledge the work that everybody who supported this team, as well as their peers that were out running other experiments that we didn't showcase tonight. So that it's really been a WHOI-wide response, and it's been something really to see. And I think the Endeavour cruise was kind of a microcosm of all the things that had to be done quickly. I think it's also important to point out our sponsors. NSF was mentioned, the Coast Guard, NOAA, BP. Were there any others that have provided some sponsorship to help? EPA. And also our trustees have supported us with advice, and we've had some what we call the oily trustees meetings to make sure that we're not running amok, and we really appreciate that as well. So I wanted to make those points. But thank you for the panel. You guys did great.